Hello AP, this is section 12.6, a model for chemical kinetics. So molecules must collide in order to react. This means that they have to make physical contact with each other. Only a small portion of the collisions produce a reaction. So not every time molecules collide is there going to be a reaction. They don't always react. Activation energy, this is the energy that must be overcome in order to produce a chemical reaction. So why is activation energy needed? The particles need energy to break existing bonds and form new bonds. Some things that you can do are increasing the temperature. This increases the reaction speed. The rate of constants often double for every 10 times the increase in temperature. So one thing we know about molecules is that the higher the temperature, the more kinetic energy they're going to have. The more kinetic energy they're going to have, the more collisions are going to happen, which then can increase the reaction speed. This plot is showing the number of collisions with a particular energy at one temperature and then a second temperature. And one thing that we also can see is that temperature 2 is greater than temperature 1. The reason why we know this is because the activation energy is lowered, meaning less energy is required for the reaction to go, so the speed of the reaction is going to be faster. So in this graph, you can see like there would be collisions of molecules that are happening all underneath this pink curve. And then there would also be collisions that are happening all underneath this blue curve. And one of the things that is shown here is our number of collisions are increasing. Our energy is increasing going this way. So what we said is not all collisions react. Only a small number of these collisions will react. These collisions here can react. The collisions on this side cannot react. Because they don't have sufficient activation energy to produce a chemical reaction. There are two factors that determine if a reaction will occur or not. And the first thing is sufficient energy. The second thing is proper molecular orientation. So the rate of the reaction depends on the activation energy. This is not the same as the delta E or the change in energy. The change in energy has no effect on the rate of the reaction. The higher the activation energy, so that EA is activation energy, the higher that is, the slower the reaction at that temperature. Now, what I want you to think about is that looking at this picture over here, we have this hill, and this guy is trying to push this boulder up the hill in order for it to roll down. The higher this hill is, the longer it's going to take in order for that boulder to roll down the hill. So the higher the activation energy, slower the reaction. The lower the activation energy, the faster the reaction. Molecules in collisions have varying energies, and as temperature increases, more collisions will have sufficient energy, because again, they're moving faster with a higher temperature, to overcome that activation energy. As the temperature doubles, the fraction of effective collisions increases exponentially. So again, there's two factors that determine if a reaction will occur: sufficient energy and proper molecular orientation. So let's talk a little bit about proper molecular orientation. Here are some possible orientations for the collision between NOBr molecules. So you can have all the atoms lining up vertically and these two colliding. And when these collide, the reaction produces a bromine molecule and then two NO molecules. So this first orientation, this works. It produces the products. Second orientation is we can have those atoms lined up horizontally. Collisions occur, and we produce that bromine molecule and then our two NO molecules. So this also works. Another orientation, they're still lined up horizontally, but the bromines aren't oriented in a way that they can collide with one another and then react. So this does not work. So the way things are oriented does make a difference. Reaction rate is smaller than would be predicted for the number of collisions having sufficient energy to react. And this happens because of the molecular orientation. So just because there's a high number of collisions happening, if they're not oriented correctly, it's not going to affect the reaction rate. The Irenaeus equation can be used to calculate the activation energy. So as activation energy increases, this means K, this is our rate constant that we've been using, is going to decrease. The Irenaeus equation describes a line. We can plot 1 over the temperature versus the natural log of K and get a straight line whose slope is negative activation energy divided by R, which is a constant. And here it shows you the straight line, and the slope is the negative activation energy divided by R. So let's define the Irenaeus equation a bit further. The natural log of K is equal to the natural log of A minus EA divided by RT. So K, this is our rate constant. R is a constant. It's 8.314 joules per Kelvin times mole. T is in temperature, is your temperature, but it has to be in Kelvin. And then A is a frequency factor. It's constant as the temperature changes, and this would be given to you in a problem. And then EA is our activation energy. A variation of the Irenaeus equation can be used to calculate the activation energy or to find the rate constant, okay, at another temperature if the activation energy is known. So this is the natural log of K1 divided by K2 is equal to the activation energy divided by the rate divided by R times 1 over the second temperature minus 1 over the first temperature. So let's look at an example using this. The rate constant of a first order reaction is 3.46 times 10 to the negative second s to the negative first at 298 Kelvin. What is the rate constant at 350 Kelvin if the activation energy for the reaction is 50.2 kilojoules per mole? Okay, so we have K1 here, we have T1 here, we have T2 here. We're trying to find K2, and we have our activation energy here. So one thing I want to point out to you is that our activation energy is given to us in kilojoules per mole. And if you remember, our R constant is 8.314 joules per Kelvin times moles. So it's usually beneficial to go ahead and convert this to joules because you need to have the same units here. So move your decimal 3 places to the right, and you're going to get 50,200 joules. There are 1,000 joules in 1 kilojoule, so you could also do 50.2 kilojoules, 1 kilojoule times 1,000, and you'll get the same answer with that. So the natural log of K1 is 3.46 times 10 to the negative second s minus 1. We do not know K2, so we're going to leave that there, is equal to our activation energy, which we found to be 50,200 joules. And our R is 8.314 joules divided by Kelvin times moles times 1 over T2 is 350 minus 1 over 298. Okay, so I'm going to calculate this side of the equation and rewrite this here. So this side equals negative 3.01. So in order to get rid of that natural log, I'm going to use the E to get rid of that. Do it to both sides, cancels out over here. So that leaves me with 3.46 times 10 to the negative second s minus 1 over K2, and that equals not 3.01, it equals 0.493. And then solving for K2, K2 is going to equal 7.02 times 10 to the negative first 1 over s. So the last thing that we need to talk about is catalysis. A catalyst is a substance that speeds up a reaction without being consumed. It produces a new reaction pathway with a lower activation energy. So it allows the reaction that's already occurring just to happen with lower activation energy. The catalyst lowers the activation energy for both the forward and the reverse reaction. So here's a diagram showing this. The reactants start here. Without an enzyme, you need a lot more energy in order to form the products. And then with the enzyme, it's almost divides the energy needed, the activation energy needed in half, or a little bit more to produce those products. So there are enzymes that are biological catalysts, such as the enzyme hexokinase. So this has an active site, and it binds glucose and ATP. It binds to the enzyme. It converts them into products, producing glucophosphate and ADP. And then, so those are released, and then you still have this enzyme that remains, so it hasn't been used up. There are also types of inorganic catalysts. Homogeneous catalysts present in the same phase, reacting molecules. This is usually the liquid phase, and the heterogeneous catalysts exist in a different phase. usually involves gaseous reactants being absorbed by the surface of the solid catalyst.